Okay, so I did talk a little bit about this, that there are many reactions that are just not as simple as we led you to believe. So, those of you that would have taken um, biology, you talk a lot about mechanisms. Glycolysis as a mechanism, the electron transport chain, and basically what it means is that a reaction is a complicated process that occurs as more than one step. So similar to like a Hess law question, right, where you had more than one step to get a target reaction, that overall system of equations is called a mechanism. So what we're going to do today, we're going to do two things. Three things kind of. We're going to propose a mechanism and look and see if it's reasonable. We're going to look at how to better represent a mechanism using potential energy diagrams. So yesterday we did Maxwell-Boltzmann, which is kinetic energy and number of particles. So now we're going back to potential energy, which sometimes students find a little bit confusing to switch back and forth, but we'll stay calm and do our best. And we are going to look at when you have a mechanism, then there is something called the rate determining step. So one of the steps in the reaction mechanism will be listed or labeled as slow. And that slow step determines the rate, or limits how fast the reaction can go. There's kind of a terrible saying, you're only as strong as your weakest link, but it really applies here. If a reaction can only go as fast as its slowest step, okay? So we're going to do a bunch of things today to consider what happens when you have a reaction that occurs as a more complicated process than just one straight up reactants make products. So each step, so in Hess's law questions, we labeled them like 1, 2, 3, 4, okay? So those would be considered steps. A fancy word is an elementary process or an elementary step. That's the same thing. And then overall, it's called a mechanism. So one of the things we are going to do is look at each step separately and see if the steps themselves are reasonable. So we haven't really considered whether we write reactions that make sense, that are reasonable. But if you notice, say you have combustion, single displacement, double displacement, what are some other common ones? Even neutralization, all of those have two reactants. And that's not random. When you are trying to get particles to collide together for a reaction to occur, if you have many, many, many molecules trying to react, that doesn't make sense. It's not going to work. So reactions can either have one reactant, two reactants, or very rarely three. So a unimolecular reaction means one reactant. Collision of two molecules or two reactants is called bimolecular. And then three is called termolecular. So that's very rare. And if you think about it, it's like, oh yeah, combustion, single, double displacement are all two, right? One reactant would of course be decomposition. That's a thing too. But decomposition reactions are either so reactive that we don't really practically do them in a high school lab, or they're so endothermic, like so much energy has to be absorbed that it's just not feasible either. What's the point of putting so much energy in? We don't want that, right? We would prefer exo. Okay, so this is one of the criteria we're going to use. And So in the thermo unit, when something was a reactant on one side and in a step, and a product on the other, and a product in another step, or vice versa, what did we do with them? We crossed them out. And we did not include them in the overall target equation. We didn't really talk about those extra substances and what they were, but they are intermediates. They're in between. So they are not considered to be overall reactants and products. So then if you're looking at the surface of an equation, who really cares what happens in the pathway? We just care about the reactants and the products, and that's literally the definition of Hess's law. When you want to look more in depth at a reaction, then you should really consider what is going on in between. That makes you a better chemist, okay? So reaction intermediates are not reactants and products. They are not found in the overall target. So in what did we do last unit? We canceled them out, okay? And then another type of molecule that is important when you look deep into a reaction is called the activated complex. So the word activation, like if I activated you to get excited about chemistry, what would you do? You would have lots of energy, and that's what an activated complex is. It has the maximum potential energy, which makes them unstable. So draw a really quick sketch. It does not need to be big, okay? Actually, don't even label the bottom. So for potential energy, where would the activated complex be? It would be up there, okay? The maximum potential energy possible. So when we do our example that has, you can see it there, we're going to label on that potential energy diagram where would the activated complexes be and where would the reaction intermediates be. They're still sort of considered to be a bit theoretical because they're in the in-betweens. So just like with this picture, we don't draw it to scale. So you don't really have to say what is an activated complex, what is a reaction intermediate, just where would they show up? Where would we theorize them to be? If you're given a mechanism, you can figure out which is which we'll do once we look at the catalyst notes. But for now, we're just going to sort of say where they're at, okay, in our picture. So logically, if you have a mechanism, then one of the steps is going to be the slowest. And you don't even have to worry about trying to think about it. Is it 5 minutes compared to 2 seconds? It'll literally say fast, and one of them will say slow. So if you had 4 steps, it could be fast, 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 slow, slow, fast, fast, whatever. It's literally going to be labeled slow. So the reaction can only go as fast as the slowest step. Again, the unfortunate analogy, you're only as strong as your weakest link. So if you have a mechanism that is going to complete your reaction you're looking for, and step 1 takes 2 seconds, step 2 takes 2 seconds, but step 3 takes 45 minutes, who cares that the first 2 are fast? You're going to be limited. You're going to have to think in your head, I need to give at least 45 minutes for this reaction to occur. So it limits how we think about the overall reaction. So there are 2 types of rate law questions. We did one where you had to figure out the power, where you're given the chart of data. Another way to do the rate law, if you have a slow step, you can use the slow step. So this is much, much, much easier. Okay? If you want to remind yourself, what does a rate law look like? And then we only care about reactants. And we figured out what the exponents were, right, with the chart. This is general, sorry. So here, we're given a mechanism. If you want to label these as 1 and 2, so it looks more like what you did last unit, you totally can. Step 1, A plus B makes AB. That's a fast step. Step 2, 2AB makes C. This is the slow step. So if you are asked to write the rate law, you're going to use the slow step. The reaction can only go as fast as its slowest step. Okay? So then we do the same thing, rate. Don't forget the rate constant. We only care about the reactants. And then the other type of question, we would have had to do the data and then figure out, like, say it was doubled and the rate was quadrupled, then write it as a 2 to the power of 2. This is so much easier. All you're going to use is the coefficients. So this is a 2. I get to make this a 2. Isn't that wonderful? So whatever's in the slow step, so this, there's only one reactant, there's only one term in the rate law. If this step number 1 happened to be the slow step, then you would use A and B. Always however many reactants there are, okay? So this is one type of question you can do, but it's very straightforward. As long as you remember to use the slow step, then the coefficients become the exponents, and that makes your life much easier than doing that chart way. Are you going to have to do both? Yes, but we like this. Okay, so the second thing we're going to do is take another look at potential energy diagrams. So this is a very fancy diagram. Hopefully yours is a good size on your paper, right? So I chose this one on purpose. Now, first of all, they wrote EP here. We usually write PE, but that's fine. Okay, it's just potential energy. So it says this diagram has 3 peaks. So that means there are 3 steps in the mechanism. So if you want to label those, 1, 2, 3. So when we looked at a potential energy diagram before, these were the reactants, and then all it did was make some kind of products. So now, when you have a mechanism, you start with the overall reactants, and then they make something that then is consumed to make something else that then is consumed to make the overall product. Okay? So it's not one hump because there is more, or peak, because there is more than one step in the mechanism. The other thing we did, one of the other things we did with the potential energy diagram was draw where was the activation energy. So I wrote what we did last unit. Okay, so we're going to do the same thing we did as the thermo unit, but now, because we have 3 peaks, how many activation energies are there? 3. So you always start at the reactant line-ish. So 3 peaks, 3 steps, 3 activation energies. So the third point says, activation energy is how much potential energy required for a reaction to occur. That's the same definition from the last unit. So if you have more potential energy required, then it is logical that that will be the slower reaction. So if you look at this one is exaggeratedly much more bigger, and I encourage you to do that. So here, this is much bigger than these two. So which one is the slowest step? Step number 1, because it has the largest activation energy. It's the largest. If you put the highest, that's fine too. So if you go the other way and you're given a mechanism and you have to draw the diagram, make it exaggerated, okay? So let's say you had a mechanism, you can write this down or not. Let's say you had step 1 was fast, step 2 was slow, step 3 was fast. Then when you go to draw your picture, make the slow step obviously the biggest. Okay, exaggerate which one is the slowest. It does not need to be the first step. It has to be the largest peak, okay? So again, I chose this picture kind of on purpose. So we can show on a potential energy diagram where the activated complex is and where the reaction intermediates are. Is your hand up? Okay. And again, we're not really focused on what is there. We're just going to say where they are. But this picture, it does have these diagrams here. So I just wanted to show you this kind of notation. One of the things that you can do, especially if you continue with like biochemistry and organic chemistry, They often write intermediates with this notation where you have square brackets and this weird sort of double plus. It's called a well, if it's carbon, it's called a carbocation. You can kind of see that the lines aren't really very solid. It's trying to show that it's sort of being broken and it's not really formed. These are intermediary substances. So I don't expect you to do that, but if you see that kind of thing, that's what it means. What I want you to be able to do is say where the activated complexes would be. Do you have to say what they are? No. Okay? So pick a different color. I'll do orange. So activated complexes are found with the maximum potential energy possible. I'm going to call those AC. They're going to be at the top of the peaks. So how many activated complexes should you put in? 3 peaks? You should put 3. Do you have to say what the activated complexes are? No. Never. Let's pick green for intermediates. Nice little Christmas with the green activation energy. I'll call these Ri. So if the activated complexes are transitions at the peaks, then the reaction intermediates, by definition, are produced in one step and then consumed in the next. So they would be in the valley, because now so put in some reactants, it makes whatever's here, then those get used up to make whatever's here, then those get used up to make the overall, okay? We're going to do another more normal example on the next page. Bless you. Okay, we good? Okay, so this is a potential energy diagram. I forget if it's from your textbook or a similar Ontario version textbook. So now it's labeled more like what we're used to, okay? It says write the overall reaction. So in here, in the old unit, thermo unit, I said you could have written reactants and products just like that. You can still do the same thing, but it does tell you what these are. I think it's already balanced too, which is nice. So it also revisits the idea about delta H, the difference between the R and the P line. But that's from thermo. We don't need that here. Sorry. So how many elementary processes or steps are there? What do you think? How'd you know that? Good. Okay, so 3 peaks equals 3 steps. Okay, so again, activated complexes. which in this graph or diagram, it doesn't give any indication what they are. That's totally fine. We're just going to label, I'm going to call them AC. You can call it whatever you want. They are at the top of the peak. They have the maximum amount of energy. And then same thing, reaction intermediates, I'll call them the same, Ri. They would be in the valleys because they're produced and then consumed. So when you're given such a limited amount of information, it doesn't tell us anything about what the mechanism is, whether it's fast, slow, whatever, we don't know. So the only thing you can do with this picture is take a look at the activation energies. So for the rate determining step, that's the slow step. Okay, it'll have the largest activation energy. So you can do the same thing and go and draw them in. Do we care that these two, activation energy 2, activation energy 3, are very close together? It's hard to tell. No, we don't care. Why? Because this is obviously the largest. Okay, so like I said, if you're asked to draw a diagram, make it as obvious as you possibly can. So sort of similar to the diagram yesterday, we can't really do much. There isn't exact numbers on here. It doesn't tell us what the activated complexes are. We can just analyze what we can. Where would they be found on the diagram, and which step is the slowest? Okay? And then the last question we're going to do, or last example, is determining the reasonableness of a mechanism. So the annoying part here is there are 3 criteria, and you have to remember all 3. Also, so you're going to say whether their criteria is satisfied and give a really brief explanation, which means if there's 3 of them, worth 2 each, that's 6. And then saying if the overall mechanism is reasonable, is worth a mark. So this question is out of 7 marks. That's a lot, right? So, you know, these questions are kind of beefy, and there's a considerable amount that you have to remember how to do, okay? But the criteria themselves are not too difficult to figure out. Okay, so what I want you to do is highlight them. Better than I did. Because you can't ask me, Miss Todd, I don't remember the criteria, can you tell me? You have to know these. Now, do you have to do them in this order? No. Okay? But this is the order that I give them to you. So the equation for the elementary steps must combine to give the equation for the overall reaction. What does that mean? It's sort of like super easy Hess law. You don't have to multiply, you don't have to flip. All you're going to do is cancel stuff out if you can and then add them together, okay? And it sort of makes sense. If you flip stuff around and change the coefficients, then you're basically changing the mechanism and you're sort of like, wait a minute, that means what I proposed or the scientist has proposed isn't reasonable, right? Okay, so no coefficients, no flipping, just as is, cross stuff out and add them together. The second one says the proposed elementary steps must be reasonable, and that goes back to the first slide. So each step can have 1, 2, or at most 3 reactants, no more, okay? You can just write 1, 2, or 3. You don't have to put unimolecular, bimolecular, but if you want to use those words and sound fancy, that's fine too. And then the last one, again, as long as you remember what the criteria is, it's pretty straightforward. So the experimentally determined rate law is given. So some scientists did the chart method. You have to do the rate law using the slow steps, and see if they match. So these questions are also unique because if you look at the next page once you're done writing this down, it gives you tons of information and it literally says determine if the mechanism is reasonable. So there's no question, what do I do in this question? As long as you remember the criteria, and again, you don't have to go 1, 2, 3 in this order, you just have to do the 3 and then write a final statement. All 3 criteria are satisfied, mechanism is reasonable. Criteria 2, not satisfied, mechanism unreasonable. If the question on the test is unreasonable, again, because you're going to get 2 marks for each criteria, go through all 3 and then say yes or no, okay? To get your full 7. Because it is pretty easy 7 marks as long as you remember what to do with the criteria. They're not tricky. And the question is very obvious. You're given a mechanism, given a rate law. It says determine if the mechanism is reasonable. And I'm going to do the example. I'm just going to go in this order, okay? So consider the reaction below. So you have to be given the target. In order to check if it's going to match the mechanism, you have to be given the rate law. Sorry for this unfortunate formatting. And you have to be given a mechanism and one of the steps labeled slow. So there's quite a bit of information that has to be provided to you. And then the question says, determine if it's reasonable. And, you know, it would say like 2 mark sheet criteria, total 7, whatever. So I would try to hopefully give you an indication to remind yourself, oh yes, the 3 criteria. So do these steps combine to give the overall equation. So remember, no flipping. We don't want to flip or anything because we want to see if what's proposed works, okay? So let's see. N2O is on both sides. I think that's it. The rest of them we're going to add, right? So add it up. 2NO, 2H2. So far, so good. N2, 2H2O. Does it match what you're given? Yes, it does. If you don't like the wording in my sentence, you don't need to copy it verbatim, okay? Give some sort of reason. The steps combine to give the overall target, therefore the first criteria is satisfied, something. Criteria 2, we're checking each step, okay? So step 1, how many reactants does it have? Just reactants, 1, 2. Step 2, 1, 2. Is 2 okay? Yes. 2 is okay, 3 is okay, 4, no, not okay. I'm going to use the word bimolecular just to, because, you know, let's be fancy. Again, there's different things you can say, less than or equal to 3 reactants, that's fine too. Okay, and then criteria 3, we have to use the slow step. And again, it's not even going to make you decide 5 minutes, 10 minutes, 20 minutes. No, it's going to say slow. And because we are only given the mechanism, we can't do the chart way. We can just use the slow step, use the coefficients to write a rate law. So we have NO. Actually, What should its exponent be? 2. And h2, and its exponent is 1, not 0. Does that match the rate law we're given? NO squared, h2 to the power of 1. It sure does. Okay? This also sort of emphasizes the whole idea behind a mechanism. Why doesn't the rate law match the overall target? Because the target equation occurs as a series of steps. Okay? So if all 3 criteria are satisfied, is the mechanism reasonable? Yes, and write a sentence. Sorry. Yes, but go through them all so you get full marks. On the worksheet, sorry, there are both kinds, unreasonable and reasonable mechanisms. This is a pretty beefy question, so there wouldn't be both kinds on the test. I would just pick one. And to be honest, I've done both. So see how I'm feeling when I make up your test, you know? So please, 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 please try those questions on the worksheet I gave you yesterday. On the review worksheet, it says that that worksheet is good review. The answers are on the back of the worksheet. The review answers, I put them up here and on the green board and on D2L. But if you're not a fan of D2L, you can definitely take pictures before you go. Okay? So we have a significant amount of time before lunch. You can